Good morning, Doctor. I am Bu Ying Ki. Here is our mini project presentation video for control system. According to the question 1, a transfer function was built. The numerator of this transfer function is negative 30 times negative 2 plus s times negative 10 plus s, while for the denominator is 1 plus s times with 12 plus s times with 5 plus s. This transfer function consists of one k value and two zero and three poles. The k value for this transfer function is negative 30, a is equal to negative 2, b is negative 10, and so on. According to question 2, to obtain a kjj omega transfer function, the s was replaced with the j omega, and the last answer for the transfer function is as shown in the figure 1. Therefore, the transfer function was separated into its constituent parts. For log amplitude plot is as shown in figure 2, while the phase plot is as shown in the figure 3. By using Scilab, the amplitude response and phase response was plotted as shown in this graph. The gain margin for this system is negative 20, phase cross frequency is 0, phase margin is negative 32.69, and the gain cross frequency is 4.61. As shown in this graph, this system has negative gain margin and negative phase margin. Therefore, the stability of this system is unstable. By using the phase lead compensator to improve the 10% of the current phase margin of the response, first we need to find the new phase margin, and then the phi max, alpha value, and the tau value. After finding the alpha and tau value, we will substitute to the transfer function, and the last answer of the transfer function is as shown in here, which is 1 plus 0.0424 s per 1 plus 0.0281 s. After that, we will using Scilab to plot the response, amplitude response, and phase response. And the phase margin for this system after 10% of improvement is negative 33.5, and the gain cross frequency is 6.06.
By using the phase lag compensator to improve 10% current phase margin of the response, first we have to find the new phase margin. The new phase margin has to add with the 5 degree of the safety margins. Then we're using the Scilab to find the new gain crossover frequency. The new gain crossover frequency is 4.461 Hz or 28.03 radians per second. To find the transfer function of the lag compensator, we have to find the value of the tau and also value of the alpha. Then we substitute the value of alpha and the value of tau into the transfer functions. So the transfer functions of the lag compensator is 1 plus 0.356 s over 1 plus 0.3678 s. Then we're using the Scilab to generate the frequency response and the phase response. So the new phase margin is negative 31.11, and the new gain crossover frequency is 4.46. So based on our finding in question 3 and question 4, by using phase lead method, the new phase margin is decreasing with negative 5.54%. As a result, the 10% improvement is not achieved. Then by using phase lag method, the new phase margin is increasing with 4.83%. As a result, the 10% improvement is also not achieved.
By comparing the result, the lag compensator was able to achieve a larger improvement in the phase margin because the percentage of increment of phase lag compensator is 4.83%, while the phase lead compensator is negative 5.54%.
Based on the transfer function that we built, when Implementing the phase-lead compensator, it should generally increase, but the new phase margin is smaller than the old phase margin after applying a lead compensator. Therefore, we can conclude that this compensator has not been properly designed or implemented. On the other hand, although the phase margin needs to have an improvement by 10%, but the percentage of the increment for the phase lag compensator is only 4.83%. It's important to note that these results are specific to the given system and specific compensator design used. In practice, the choice of compensator depends on various factors such as the desired system response, stability requirement, and other design constraints. That's all from our group. Thank you.